All right. So we're going to hold questions till the end of Elijah's talk, but hello, everyone. Thank you for joining DataCon LA 2021. Welcome to the AI ML Data Science track. My name is Eli, your host, and our co-host today is Stephen. We'll be moderating the chat and for your session today. We have our guest, Elijah Ben Izzy, and he will be talking about enabling simple ML ops at Stitch Fix. He is data platform engineer at Stitch Fix, and Elijah has always enjoyed working at the intersection of math and engineering. More recently, has focused his career on building tools to make data scientists more productive. At 2 Sigma, he was building infrastructure to help quantitative researchers efficiently turn ideas into production trading models. At Stitch Fix, he is a founding member of the Model Lifecycle team, a team that focuses on streamlining the experience for data scientists to create and ship machine learning models. In his spare time, he enjoys geeking out about fractals, looking at antique maps, and playing jazz piano. Without further ado, I'll hand this over to the speaker. Thanks for being here, Elijah.
All right, thank you so much, Eli. I'm going to share my screen, and then we can get started. Cool. All right, I'm super excited to be here. Hello, everybody. My name is Elijah, and I'm going to talk about how we enable data scientists to do machine learning operations really easily at Stitch Fix. The talk is called The Function, the Context, and the Data, and we'll kind of get to that in a bit. All right, so what's on the agenda today? First, I want to talk about Stitch Fix and data science at Stitch Fix. Who are we, and why do we keep showing up at machine learning conferences? Next, I want to talk about some common workflows and motivations for data scientists at Stitch Fix, sort of what the problem is that the data platform team wants to solve. Then I want to talk about representing a model, which is sort of a really interesting problem we have, and how the representation of a model we built for data scientists can unlock a bunch of capabilities for them and sort of make their work easier and really give them this simple ML ops for free. Then I want to end up with talking a little bit about where we could go in the future and some interesting things we're thinking about. So if there's one take home that I want you to get from this, it's that building the right abstraction can enable separation of concerns between data scientists and platforms. And I'm going to talk about the separation of the abstraction that we built and how that sort of enables the separation of concerns. But if there's one thing I want you to take home, it's the right abstraction, some ideas of how to build it, and this concept of separation of concerns, which I think is really important. Cool. So a little bit on myself first. I was already introduced, so I can fly through this. Grew up in Berkeley, California, went to Brown. I studied applied math and computer science. As Eli said, I've always been interested in sort of the intersection of math and software engineering, building systems to express sort of interesting, complex mathematical relationships. I then worked at 2 Sigma, doing just that, building tools for data scientists, and now I work at Stitch Fix, also doing that. And it's a really interesting space to work in, and I want to talk a bit about it. All right, who are Stitch Fix, and why does a clothing company end up talking at a lot of machine learning conferences? So Stitch Fix is a personal styling service. There's sort of 2 ways to work with a platform. Well, first, you create your style profile for both of them. You tell us like things you like, things you don't like, things you're excited about. Give us data and information so we can get you the right items. Then there are sort of 2 ways to work with it. One is you get a box on a regular cadence or whenever you want of 5 hand-picked items that are picked for you by a combination of a stylist and an algorithm, right? So the stylist works with the algorithm to get you things that we think you'd like. You keep what you like and send back the rest. We also have an option to shop at your own personal curated store and check out what you like. So we have a store and we think, oh, all of these things we're showing you are going to be really good because of our data science and algorithms. So in both of these ways of working with it, there's sort of a feedback loop where we can gather data. So when you keep what you like, you send back the rest, we can learn more about it. When you check out what you like, we can learn what you like from what we've shown and what you don't like. So it turns out there's a lot of data behind the scenes here and a lot of things that are really fun and easy to analyze. Oh, fun and interesting to analyze, I should say easy. So to build on that, data science is behind everything we do. And we actually have a whole organization dedicated to data science. It's called the Algorithms Organization. It's 145 plus, and more now, data scientists and platform engineers. And there are 3 main data science verticals in the platform team that it's all built on top of. There's merchandising and operations algorithms, that's sort of handling, moving inventory, clothing, et cetera, from warehouse to another, figuring out how to do that optimally. There's client algorithms to make the client happy, and styling and CX algorithms to help sort of the styling and customer experience part of the equation. And they all build tooling and stuff built on top of the data platform. So I'm not going to tell you all the interesting things about Stitch. I want to get into the specific problem that I'm working on. But if you're interested, there's a great visualization online. It's called Algorithms Tour. If you Google Stitch Fix Algorithms Tour or go to algorithmstour.stitchfix.com, you'll be able to find it. And that's a really interesting way of sort of looking through this that goes into depth on each of these pieces of the puzzle. All right, so what does data science at Stitch Fix look like, and how does it differ from other companies? What makes our problem interesting and unique? So first, I'm going to tell you about what data science is not like at Stitch Fix and sort of a common approach to data science that I've seen at a few different companies. So it's sort of a typical organization. You might have horizontal teams. So you'll have like a software engineering you'll have a horizontal team. Like a software engineering team, a data science team, a data engineering team, and each one of them is maintaining a sort of specific piece of technology. And to get something out into production, to get an algorithm into the business, you do a handoff. So data science might do some proof of concept, write a white paper, pass off to engineering, they implement a model, then they like talk to the data engineers and they get the data and build the ETLs for them, and that's how you get a model into production. There's a lot of coordination required here. And at Stitch Fix, we actually want to avoid this entirely. So at Stitch Fix, we have a single organization for all of algorithms, and there are no handoffs. So it's not like one person will come up with an idea and the other person will implement it. The person who comes up with that idea is responsible for owning it end to end, so for getting that idea out into production. And we have a lot of data scientists here. As I said, more than like 100+ data scientists, and we really need this process to be able to scale. So to do that, it's all built on top of these data platform tools and abstractions, which I'll dig into more. All right, so gave you the setting, talked a little about Stitch Fix. Now, what's the problem that we were actually trying to solve? And why am I talking here? So the problem comes with these verticals I just described, these sort of data science verticals. When a data scientist is expected to own an idea and get it out into production and sort of deal with manage that whole stack. So saying data scientists are full stack, which is kind of a mantra that we live by, and I sort of just talked about in the last slide, doesn't actually mean the data scientist builds the stack from the ground up. So just as a software engineer would not always be writing in C, they'll be writing in Python and higher level languages, or they won't always be writing in assembly code. We want to give sort of these higher level languages to data scientists. So the goal is to allow them to scale without more complex infrastructure that they have to manage and maintain, and without more cognitive burden. So we want to be able to improve the breadth of what they can add to the business without making it that much trickier to think about the infrastructure. So data scientists should always be full stack, because then they should always have ownership over everything that they do and not have handoffs. But can we shorten the stack? So this is why we build a machine learning platform, and what we build to make it easier for data scientists to do all these things and get their models out into production. All right, so let's take a look at some data science workflows. The training, so this is a common workflow starts with training. This is sort of run at a regular cadence. We retrain our models every night, every week, up to the data scientists. They'll write an ETL. This will save a model blob on S3, some sort of serialized artifact, and then copy it to production. That's what every data scientist does at Stitch Fix. And then there are a few options of what you can do when it gets to production. So we had these processes before we came along, sort of well-defined. You could build a model microservice, so serve a model in either serving customer recommendations, giving data to the stylist to help make decisions, run predictions in batch, so that's generating perhaps recommendations over all customers, and running in a streaming setting. So when a feature gets updated or you get a new customer coming in, you want to generate some new recommendations for them. These all have nice and defined processes, and most data scientists kind of do very similar things for these. And it gets a little more complicated when you get into the analysis side. So wanting to track metrics on your model, everybody has different things they want to track, and sharing stuff with other teams. So how to share a model with other teams, how to sort of share these data dependencies. This is kind of what the workflow looked like. I'm going to think about optimizing it. So the goal is to build an abstraction to give data scientists all of these capabilities for free. So if they build something to the abstraction that we give, then they can get all of these capabilities for free or with a little bit of configuration. So the caveat here that I think is interesting, and unique but not entirely unique to Stitch Fix is we have largely uniform workflows with independent technologies. So as a platform team, we don't really care if a data scientist wants to use TensorFlow, scikit-learn, PyTorch, Stan, whatever. It's up to them. They're actually best at deciding. And this is kind of where separation of concerns comes in. Data scientists are concerned about which tooling to use that's the best to solve their problem, and platforms is concerned about making it really easy to get that into production. So looking back at our problem, we've got this black box, this thing in the middle, this abstraction I want to talk about, that allows us to give all of these things for free, right? Build model microservices, run predictions batch, track metrics, streaming predictions, share with other teams, etc. So what did we actually do? Well, the question is to build or buy, and spoiler, I'm talking to you, we decided to build, so I'm giving a talk about it. But first, hats off to a few of the sort of really interesting prior work. So MLflow, TensorFlow Extended, ModelDB. We talked to the people in this project and learned some really interesting things. But we decided to build our own for some specific reasons that I'll go over. It gave us seamless integration with current infrastructure and leverage. So we already had a fairly sophisticated set of tooling that you can build a machine learning platform on top of. We didn't need to reinvent the wheel, and we could use that and get a lot of leverage out of it. Our model tracking and management sort of data model wasn't necessarily standard. So we have a lot of different segments and varying ways to slice and dice your models. You might want models for different experiment variants, models for different regions, for different business lines. And we wanted to make it really easy to sort of like chop those up and say, like, I want this specific model to serve this specific group of customers. And we found that these ones were a little more prescriptive about the ways that you slice and dice your models. Having a custom build allows for pivoting as needed. So we invested in interface design to allow for plug and play with various open source options. So really thought about how to build the interface between internal components so that if we liked something we had from the outside world, we could take it in and use it. And we called it the model envelope. Data scientist sticks their model in an envelope, sends it to platform, and we can do whatever they want with it. All right, so what we built, the idea is the data scientist only writes the training script, and the rest is configuration driven. So import your Python libraries, train your data. This should all look fairly familiar to data scientists. Or sorry, load your data, train your model, and now you're done with your ETL, and this is where you're like, okay, I got to do something with my model. So you save it to our centralized registry. Pass in a few parameters, I'll go over some of them later, and then log some metrics, and you're good to go. You got the model transferred, and it's now out of your hands into the platform, into the envelope. So this envelope then goes to this notion of a model envelope registry, which is basically a model envelope database that stores all these models with enough information to give us all of this stuff for free. And I'll talk about what that looks like in just a bit. So the database stores models, and we wanted to know a way to represent it, or a way to say, here's all the interesting, necessary information you need on a model to give you these other pieces for free, or to make it really easy to sort of hook into the platform tools to build a microservice to run predictions, etc. All right, so I'm going to take a step back, and in talking about how we represent a model, I want to use a metaphor and talk about writing a recipe. So I'm going to say there are three critical ingredients, or three critical components of writing a recipe. There's the instructions. This is what you actually do and how to cook it. There's the cookware. This is sort of the context or the extra things you need that aren't food or instructions to run it, and the ingredients. You need to match the ingredients to write a recipe. And if you have all of these three things, sort of a good representation of them, know the right ratios, know the right cookware to use, and I want to say you can cook this recipe in any context you need. You can cook the recipe for yourself for lunch. You can cook it for a dinner party. You can cook it and keep it to go. It becomes a fairly flexible thing once you have this nice, concise representation of it. And let's tie that back to how we represent a model. So the function, this is what the model does. The actual sort of like guts of it, the code that the model runs to process the data. The context, this is where and how to run the model. The environment, everything about that. And the data, this is the actual data that the model needs to run. Garbage in, garbage out, you need good data to write a good model, to run a good model. And once you have these three things, you can kind of do whatever you want with the model. So I'm going to talk about what each one of these means and talk about how we take these different pieces of the model and use them to give all these capabilities to data scientists. So the function, this is the artifact and the shape. What's the artifact? Well, for us, it's the serialized model, the bytes, including the state, and any metadata you need for serialization. So how does this work in the platform? Well, think separation concerns. Data scientists are responsible, obviously, for training the model, for training the object, and they pass it in to this save model function. Platform serializes and derives any metadata they need to deserialize it later. The data scientist passes the model in, and platform can do all the rest. They just give us an object, and we're good to go. And the shape. This is the function inputs and the function outputs. So what does the model take in, and what does the model take out, or give out? So data scientists pass a sample data frame or specify type annotations. We also have an API that they can give a function with type annotations. And platform serializes and represents these in a custom format. So this is cool because all data scientists have to do is give us a data frame, and we can look at the columns, determine the exact shape of the function, and now we know what their model's supposed to take in. Platform serializes this, and we have a custom representation of it that we can use later throughout the rest of our platform. All right, so then the context. This is the environment and the index. The environment is installed packages, sort of libraries it needs to use, any custom code that it needs to use that you've written sort of ad hoc, so it's not all in the same file, and the language and the version. So this makes a little more sense when you think about most of our models which are in Python, but it's fairly extensible to other languages as well. The platform can automatically derive the installed packages. So we can look at the pip and the PyPyRCon environment and say, oh, these are the exact versions of the packages that are installed. And data scientists pass pointers in if they need to. So if there's a special API where they say, oh, I want this, this, and this library, we can then look at it and freeze the specific dependencies they needed. Custom code, data scientists can pass pointers to modules, and the language and version platform can automatically derive this. So we know, okay, it's like Python 3.7, we're good to go. Again, most of this is automatically derived, separation of concerns. We want data scientists to worry about as little as possible to get their model out into production. And the index. This is sort of as I mentioned earlier, our sort of model management data model wasn't super standard. So we came up with this notion of tags to handle it. We have these key value tags that form the spine or the index of the envelope registry that I talked about. So platform derives some base tags. You got your instance name, instance description, which is about that model. We store team name and username, I think, as well. And data scientists can pass any custom tags as desired. So in this case, they pass a canonical name, but you can see a region is US and business line is women's, so you can tell that apart from a men's business line or a UK model. And this will be helpful in querying and sort of analyzing the model later. And we've got the data. So remember, this is the last piece. The data corresponds to the ingredients, and this is the training data and metrics. So training data, this is the features and the summary statistics. And what do I mean by this? Well, features are the sort of data the model actually needs, and summary statistics are sort of some metadata or information on top of those. To get these, data scientists have the option to pass some spec for features. I didn't really show how that works here, but we have sort of a little DSL to say, here's where my features come from. And platform derives summary statistics from the data they pass in, those sample data. So the cool thing about this is, again, separation of concerns. Data scientists can specify in our DSL, here's what features this model wants, and we can derive summary statistics from that and save that for later use. So they can run it in a bunch of different settings and gather those features. All right, and then the metrics. I sort of break this up into two buckets. It's scalars and fancy metrics. Scalars are like a validation loss or something like that, and fancy metrics would be like an ROC curve. Either way, it's data that's stored along with a model instance. And data scientists log the metrics here using a platform metric schema library that we built. So you can see they're logging a log loss and an ROC curve. These are all definitions that are defined by platform that's sort of centralized, pretty extensible, so data scientists can add new ones if they want. But fitting into this specific interface allows us to visualize them later on. I'll show you kind of what that looks like. All right, so we went over the abstraction in the middle there, and now I want to tie that out to all these other unlocked capabilities. Right? It's cool to say, here's how we represent a model, but how do we actually get this model into production? So let's start with online inference. This is serving a model's results in production. So when a customer logs in, perhaps they see the clothing that's recommended for them, or perhaps they're sent to some promotion or another one, depending on a model. The approach here is to generate and automatically deploy microservices for model prediction. So remember I said earlier we decided to build our own because we have a lot of leverage on top of sort of things we've built already. Well, we had a really good microservice management system, so we decided to build something that compiles down to that. So separation of concerns. What does data science do and what does platform do? Well, data scientists, they generate and test out services locally. So they have an option to like play around with the service, see what it looks like, see what it takes in, see what it gives out. They set up an automatic deployment rule. So say whenever a model with a set of tags is published, we do something with that. We deploy that model to production to this with a sort of small config saying like how it should deploy. Then they publish the model and wait. And that's where platform takes over. So platform then runs a cron job to determine models for deployment. So every 5 minutes we say like, oh, are there any newer changed models that we need to deploy that match this tag query? And then we generate code to run a model microservice. So we actually generate code that sort of compiles down to the layer that we built for microservice management and deploy models with a sort of that config they gave us to AWS. We know the right memory, the right everything. We can deploy it for them. And finally, we monitor and manage the model infrastructure. So this is interesting and a good point about separation of concerns. We've found that although we end up monitoring a ton of new services, we actually can do that much more efficiently because all the services kind of look the same and we are very familiar with how these work. So it's also a good selling point for data scientists who use our product. They don't have to worry about the quality of the service. That's kind of our responsibility and our job as a platform team. So how do we use each piece of this? Well, the function...
Just to interrupt you, a 10-minute warning for your speech time before questions.
Thank you. All right. So taking a look at offline inference, let's see how we use the function to run this model in a microservice context. So we load the serialized artifact on service instantiation and call it when you hit an endpoint. And we use the function shape, remember that we derived from the data they passed in or from a type annotation, to create an open API spec or validate inputs. So you can see here's an actual example of like, it's got a spec that we've generated. This is a microservices they can use in production. You can see there's a query function. This is just like, oh, like get one result, and a query both, which is like get multiple results, right? Each one of these has a data model behind it that validates the inputs according to what we've saved earlier. The context, we use this tag spec, as I said, to automatically deploy whenever a new model is published. Note the user never has to call deploy. It's all done through system managed continual deployment. So this is set up by those rules, and this is a nice paradigm shift for them. The stored package version are used to build the Docker image, so we can remember all the libraries that they have and those exact versions, and run that in the production environment. And custom code is made accessible to the model for deserialization and execution. So if they say, like, here's some custom code that I want, it's not part of a common library, I just want some code, we can save it in the Docker image and run it. So again, separation of concerns. All they do is say, like, here are the libraries I need, or we derive it for them, and here's the custom code I need. And we can ensure that their environment matches training exactly, which is really important and a common source of bugs if it doesn't. So batch inference. I talked about online inference, which is serving in a low latency sort of request-driven context. Batch inference is running a model over a lot of data. So generating recommendations for a lot of customers, doing back tests of stuff. It ends up being a pretty common workflow. So our approach is to generate a batch job in the Citrix workflow system. It's on top of a Airflow, which you guys might know. It's a data flow management system, and Flotilla, which is a job execution system managed by Citrix, or open sourced and sort of built by Citrix, worth looking up. And here's what data science and platform does. So data scientists create a config for a batch job. Either they want to run it locally or want to run it on Spark. Then to do that, they choose a tag query saying, oh, we want to run the latest model that matches these tags. And they say, like, data's got to come from here and go to here, the input and output tables. Then they execute it as part of an ETL. Platform, if specified, if they're going with Spark mode, spins up a Spark cluster, then loads input data and optionally joins it with features. So we have that feature spec that they've given us, and I'll tell you this in just a little bit. And if, for instance, if they have a column of client IDs, we can say, like, oh, here are the features for those client IDs, join it for them so they don't have to worry about that. Then we execute the model's predict function over the input. It's just a big map, and save that to the output table. Cool. So how do we use the function, the context, and the data? The function is the serialized artifact. It's loaded on batch job start. And we use the function shape to validate against inputs and outputs. So most of the inputs and outputs are Hive tables, meaning we can actually look at the function shape and compare that against the schema to ensure that everything's going to work before we even start running it. Then we use map partitions in PyArrow to run models that take in pandas data frames efficiently in Spark, and this is abstracted away from the user. So the cool thing about this is, again, separation of concerns. We found the fastest way to run these models, and data scientists really shouldn't have to worry about it. Not every data scientist should figure out how to run their model in batch the fastest possible way. They can just plug into our tooling, get that for free, and all they have to worry about is making their model really good. So the context. We use these frozen packages in language version in installing dependencies, similar to sort of online. We first step in the job, you install the dependencies you need. The custom code that they've saved is made accessible to the model. It's saved onto the Docker image for deserialization and execution. And the tags are used to determine which model to run. And finally, the data. So as I mentioned earlier, we use this feature pointer they give us to load feature data if they specify IDs. So if they want to call them client IDs, we can join that with the features for those clients. And we actually end up storing the evaluation table pointers in the registry. So every time they've evaluated it, they get a store in the registry, and they can look back at that table and see what they've evaluated. So we get a nice little log of it. And finally, metrics tracking, the last use case I want to go through. So we've cooked our recipe in a bunch of different contexts, and now we want to taste it. There's a little chef saying oh, I want to save some metrics on my recipe. The approach is to allow for metrics with tag-based querying. So this is where the tag data model comes into effect. So if you want to see I want to see this model for men's, for the business line, women's, for US region, for some experiment, and then some specific sort of model flavor, you would save a model with that, and then look at how that, or you save a metric with that and look at perhaps how that metric changed over time. So data scientists log metrics using the Python client. I showed you a little bit of that earlier. Explores that in a tool we have called the Model Operations Dashboard. Then saves the URL for their favorite visualization. So they can save it and share it with other data scientists, save it and update it to see if the data has changed since then, bookmark it. Platform builds and manages this dashboard. This is something that we own and that we really like to invest in. We have this capability of adding fancy new metrics types too. So if data scientists want to visualize something in a specific way, we have this library that I talked about that we can add more stuff to and visualize it. Cool. So that's sort of the workflow for metrics tracking. And I'm not going to go too much into detail on it. I'm happy to answer more questions. But I do want to show you it because it's some nice eye candy, and I'm actually really proud of what we built. So here's an example. I mean, this one's a little contrived just because the metrics are up and to the right, and normally you're not going to see it's this is not the shape of normal metrics, but I think this is your point. Each one of these lines is a model series, so a set of models that specifies a tag that satisfies a tag query, and the x-axis is time, right? So you can see we've split the models by different sets of tags. I guess it's we're filtering, staging, and prod, and then there's the tag is the model flavor there, and looking at how that model's results change over time. There's a scatter plot mode as well, so you can see how two metrics, so each dot here is a model, and you can see how, and orange is one type of model, is one set of tag query, blue is another, and you can see how sort of one metric compares to another. So for instance, if you want to see how your model is doing when you train it on a bigger sample size, you can see how the sort of loss works against the sample size. And finally, some fancy stuff. Each one of these little shapes is I was going to talk about fancy metrics. Each one of these little shapes is a model and a metric saved along with it. So there's a CDF in the middle, or no, it's a PDF, sorry. A time series at the bottom there, and then a CDF on the top. The idea is you can sort of save whatever shape you want and then compare it between models. So if you want to see how the latest prod and the latest staging model look in terms of with all your metrics, you're good to go. All right, I'll get to that question, Stephen, in a bit. The answer is yes. Cool. So in summation, and then I'll be ready for questions. There's a lot of value we get from separating concerns. So data scientists are concerned with creating the best model. So thinking about how to train a model, which libraries to use, which packages to use, what sort of model architecture to use, how many layers in the neural network, whatever it is, data scientists are actually going to be better at that than platforms by a lot. So we shouldn't be prescriptive there. Data scientists are also concerned with choosing the best libraries. So yeah, as I said, like if they want a version of PyTorch that functions most optimally for them or that has just the right feature, we're not going to tell them they can't do that. We want to support that. They're concerned with choosing the right metrics to log. So figuring out what will tell them the interesting things they need to know about their model. And platforms is concerned with making deployment really, really easy. So making it easy and straightforward to get it out into production. Platform is concerned with ensuring that the environment in production matches the environment in staging exactly. So data scientists don't have to worry about this at all. Platform is concerned with providing easy metrics analysis, so making it really easy to look through and see how their models have done. And wrapping up these complex systems, giving access to all of these sort of like complex distributed systems and data analysis workflows for free. And finally, building out behind the scenes best practices. So as in the complex systems, if we know a faster way to run Spark, we can do it and they won't even notice, except their jobs will get a little bit faster. Data scientists focus on creating the best model. This is writing the recipe. And platform focuses on optimal infrastructure. This is cooking it. So a little bit about future musing, then I'll open it up to questions. Some ideas of where we could go next. So we could think about more advanced uses of the data. For instance, production monitoring. We have all this data about the training data statistics, and we want to get visibility into how it might change from training to production. So how sort of how your data changes and what drift you observe in your features. I want to get more deployment context. So that's predictions, perhaps on streaming and Kafka topics. I alluded to this earlier, but this is not yet supported as a first-class citizen, and this is a new deployment context that you probably want to dig into. More sophisticated feature tracking and integration. So feature servers are all the rage. We're kind of starting to invest and dig in and think about how we can do that in a less ad hoc and more sophisticated way. And Lambda-like architecture. So rather than requiring a deploy for a model, can we query a system for a model's predictions? It's a really interesting idea. You have a bunch of models sort of running in memory and then query them and scale up as needed. But this requires more unified environments, perhaps. So we might want to rethink that requirement of having everything use the same Python environment, so we could run them, or everything use different dependencies, so we could potentially run them in the same process. And finally, attach external capabilities to replace home-built systems or components of our own system. So while that metric system that I showed you is pretty, it's home-built, and we have a nice set of interface or abstractions we've dived into to allow for us to plug in external capabilities if we want. So always looking into that and always interested. Cool. So thank you so much. I really appreciate you listening. If you have any questions, now is the time. You can also reach me here. Thanks.
You saw Stephen's questions,
Yeah.
so it allows for fitting of ensembles and different models.
Yeah, so it's this platform is not actually prescriptive about how we train it, right? So as long as it's a model that has some like query function, it'll fit into this platform quite nicely. And like ensembles that take in a bunch of models, there's like a nice sort of abstraction where we have this notion of a composed model. We can like say like, oh, like here's a model, and then that has like pointers to all of these other models and then can call out to them. And there's actually another platform that we've been working on. We haven't talked about it in public yet at Citrix that allows for specifying like configuration-driven training, in which this is much more a first-class citizen, saying like, oh, this model depends on this model, and you have like pointers to that model. So in your predict function, you can just like call out to these different models and do whatever ensemble logic you want. So yeah, totally supported, but not prescriptive.
Cool.
Remember, you can ask your questions in the Q&A whenever you have them. I'll ask a question.
Yeah.
So with Flotilla,
Yep.
you guys open source, um, that platform allows for the flow of jobs being created and executed. Um, what are the differences between using something like Kubeflow or something like that to run models in sort of a distributed sense? What?
Yeah, I mean, so what we were talking about there was for batch jobs specifically.
Okay.
Kubeflow is a pretty, like, it's all different approaches. Flotilla, we've ended up running, I think, a lot on top of Kubernetes, so getting the benefit of that. Flotilla is there's like Flotilla and then the Airflow on top of it. So Flotilla is the job execution system that just like, I want to run a specific job, you have a template and you run it, and then Future is so Flotilla, and then Airflow is the orchestrator that orchestrates that. Right, so similar, I think, to Kubeflow, we just ended up like different technologies, but
yeah,
we're like constantly reevaluating it too.
It looks good. I was just looking at the repo.
Yeah, it's fun. It's something I've seen in a lot of companies. Like every company has like something that runs a job and something that runs a system of jobs. And Airflow kind of took over the like system and DAG of jobs piece. But the running a job is often kind of like tied into the specific infrastructure you have. Well, if anybody else has questions, happy to answer.
And if you come up with a question later and you're watching the repeats of the recordings, you can always contact Elijah here or on all of his connected things here on the slide also.
Yeah,
so,
lots of ways to contact me. And also obligatory Citrix is hiring. A lot of interesting problems.
Okay, we've got a question.
Oh,
How did Stitch Fix land on AWS as the main service?
Oh man, that's a good question. And that was before I joined, so I'm gonna kind of wing it. I don't know if a former manager's manager of mine is in the audience, so he might, I think at least, so he might laugh at whatever I say. I think it just made sense at the time, like right, like when we were building Stitch Fix in mid to early 2010s, that was like the thing to use. It still kind of is the thing to use. It's just a really good way to build out compute infrastructure. But that said, like, could you build all these stuff on top of all the other cloud offerings? Sure, nothing inherent to AWS. We take advantage of some of their options, but it's really a lot of the company uses it. That's just kind of what we do. But there are different things that tie into different other sort of compute models as well. So nothing like inherent to that. Cool. So I'm around to answer anything else. Hopefully this is interesting. I think it's a unique problem that Citrix has of how to. A lot of people are like, oh, like I want to build something that really scales or really has like fits to a specific set of details. But at Citrix we have like often scale in terms of how many different types of models we want to support and how quickly we want data scientists to iterate. So this solution was built towards that problem, and a lot of our solutions have been. And now we're, but that said, we're always like reevaluating that as the core problem. Like, okay, it's always going to be a trade-off. You've got data science independence. You've got really need to scale to provide a quick response to customers. So it's a really interesting set of architectural challenges. You're on mute.
Eli, you're muted.
Let's try that again. Thank you, Elijah, for your presentation.
Yeah, happily.
And the attendees for their questions and interactions during the session. You can contact the speaker directly if there are any further questions regarding this topic. Please provide your feedback using the form that Stephen will provide in the chat box. Thank you again, everyone, for joining today's presentation. I hope you have gained some insights. Have a wonderful day, and thank you for being part of this year's DataCon LA.
Thanks, Hux. Bye.
Bye.